Thank you, everybody, for coming. This is related to the Aave proposal that was just passed. We would like to get people help in writing specification for the Aave protocol and explain the technology. On the team here, we have Nurit, who our VP R&D, was experienced in code security, was chief scientist in Panaya. We have Michael George, who was on the faculty at Cornell, and Yura Sherman, who's an expert in DeFi, and they will teach. And feel free to ask questions on the Zoom, and good luck to everybody. Hopefully it will be fun. Thanks.
Okay, so I'm Mike George. It's good to see you all. Good morning or afternoon or whatever time it is in your time zone. So let me share my screen here. I have a few slides, but mostly my plan today is to go through a demo and to kind of walk through things. So some preliminary things. You should have gotten an email with a Satora key and a link to the instructions for installing the prover and a link to the tutorials repository. I really want to, I believe in active learning, which means I want you guys to follow along. I'm going to ask you guys, I'm going to have some exercises. We'll take a little break partway through to give you a chance to think through some of that before we come back and go back over it. So I strongly encourage you to, to check out the tutorials repository. I'm working in a branch which I've called Aave. Right now it contains a couple of tokens and a blank specification, and what we're going to do today is sort of fill that in. But like I said, you guys should follow along and think about writing your own specifications and think about things as you go. I also want you, in addition to kind of playing with the tool and following along with our example, I think it's really helpful if you guys ask questions. That helps me make sure that you're with me. And excuse me, I think I have a little cold developing, so sorry about the throat clearing. But that'll help me make sure that you guys are following along, and I think it'll help you guys learn to use the tool, and so that's good. So feel free to just unmute yourself and ask a question if you'd like to, or you can pop a question in the Zoom chat, or you can pop a question in Discord. Yura and Nurit will be monitoring those, and will let me know if there's questions there. If you haven't had a chance to install the prover, I don't want to take time this morning to go through that. But for today's session, a lot of this you can do in the demo. Let me actually just quickly pop that up. So if you go to demo.satora.com, if you just click the ERC20 basic, I would start, so that shows you on the left Solidity code for a basic ERC contract. On the right is sort of a specification for that. I would start, if you're following along today, by just deleting everything in the spec section, because that's what we're going to develop. And then when I run the tool, you can click start verification up here, and that will do the same thing. But if you can do it using the tool, I encourage you to do that, because that'll be a more normal experience for you when you're actually using the tool. And also, the demo is not fully featured, it's just a demo. And so this will work for the specs we're writing today, but it won't work for what I have planned for tomorrow and what Nurit is planning to talk about on Friday. So so follow along today in the demo if you need to, but between sessions, follow the instructions to install things. So let me go over a little bit the plan for the workshop, the 3-day workshop, and then we can jump in and get started. So today I want to cover sort of basic usage of the prover. I want to show you how to write a few kinds of rules, and we're going to do that by developing a partial specification for ERC20 tokens. And we'll take a look at the prover output for that and use that output to sort of understand how the prover works, and also understand what's going on with our ERC20 contracts. Well, I'll get to that in a second. let me finish the plan. So after today's session, I'm hoping that you'll have learned enough that you can actually write a pretty complete specification for generic ERC20 contract. And so an exercise that I think would be a useful one for you to do between today and tomorrow is we've given you a bunch of ERC20 contracts, and it would be good to run the tool on those and try and understand the output. And in particular, we've given a couple of contracts where we've only given you the bytecode. And so one of the nice things about the Sartora Approver is it does run on bytecode. So you can run your specification against some suspicious tokens that we've generated and see if you can find the bugs in those. So that's where I'm hoping to get you to the point where you can do today. So later today, after this session, we have some office hours scheduled. I'll be there, others will be there. It'll be a good chance to ask us questions, and good time to install the prover if you haven't had a chance to, or start working through the exercise. The other two sessions, tomorrow's session, we're going to go through and think about how do I design a specification in general. So today we're going to talk about some of the features of the prover. Tomorrow we're going to say, all right, now I have a new contract. How do I sit down and think about what properties I should write for that contract? And then Friday we're going to delve a little deeper into that. Nurit is going to present some real world examples that we can work through. So before I dive in, that's all I was planning slide wise. Are there any logistical questions before we get started? All right, well, let's get started then. I have checked out here the tutorials repository. This is the on GitHub under Sartora tutorials. There should be a link in your email. I've switched to the Aave branch. That contains sort of the blank slate that we're starting from today. And there's an Aave repository inside that branch, an Aave directory that contains where I'm going to work, and an ERC20 folder in there for today's session. Inside that folder, there are several tokens. And these are just some standard tokens. We're actually going to be focusing on the interface. One of the nice properties of the Sartora Approver is that, and about thinking about rules and specifications, is that it really encourages you to think in terms of the interface instead of in terms of the implementation. And that's one way where verification kind of, I think that's true of testing as well, but I think that's nice. And we're going to also be running our examples on the ERC20 basic, which is, an ERC token that, I don't know, we read off a t-shirt or something. It's a simple ERC20. And I will be editing this ERC20.spec file.
I don't know where the
let me do this. Give you guys a second to.
Right place.
Sorry, sir.
It's not this. It's not the prover supplementary.
Here, the sleeper. GitHub.com Sartora tutorials. And he is an Aave branch.
Yeah, and I've anyway, yeah. So here's the link to the tutorials.
Okay, behind the icon, could not even get the prover installation done.
Okay. And these are, by the way, I mentioned the demo. These are the same. The ERC20 basic is the same as the ERC20 basic on demo.sartora.com. Okay. So I'm going to open up here my blank ERC20 spec file, and I'm also going to open up the interface, iERC20. I should mention there's a Visual Studio Code extension that we've been developing. It has features for being able to run the specs by pushing a button. I'm just going to use a text editor and the command line. I think feel free to play with the VS Code extension and explore the features there if you'd like. But this is how I'm used to working. So okay, so here we have the simple interface for an ERC20 contract. So these are the methods you'd expect: total supply, balance of, and so forth. And I want to start by thinking about how would we write a specification for an implementation of this interface. So in other words, what should transfer do? What should approve do? What should transfer from do? How should those relate to the view functions, total supply, balance of, allowance? And I want to write, I want to first think informally of what the properties these things should have, and then show you how to take those informal ideas and write them as rules in Sartora's verification language. Okay, so I want to start here with transfer. So if you were to look at the EIP for transfer, it says something like transfer. Let's see if I can type here. Recipient amount should transfer. Amount of tokens from the message.sender to the recipient, something like that. I think that's pretty close to what it says. And these are the kinds of properties that we verify with the prover, or at least this is one kind of property that we can verify, is to write down a formal version of this kind of property, almost like a test case, and then run it through the verifier. And the verifier will tell us when we give it a contract that the contract does have this property, or it'll give us a counterexample showing us that no, actually it doesn't have this property, and here's an example. So let's think about, or let me show you how we would write this as a rule. So I might call this rule, I don't know, transfer spec. Or I might call it something more descriptive, like transfer increases recipient balance. I find it helpful to try and think of descriptive names. I like to think of sort of the English description first, and then a descriptive name, and then start writing it. This specification is in Sartora's verification language, so it's a domain-specific language for writing specifications for smart contracts. And one of the main entry points to CVL for short, Sartora verification language. One of the main entry points in CVL is what's called a rule. And you can think of a rule as a little bit like a test, right? It's a sequence of steps that the prover should take to execute some contract methods. So in this case, what I'm going to want to do if I want to test something like this is I'm going to want to call transfer. And then I'm going to want to check the balance. Right, so I'll want to check that, balance of the recipient after is, greater than the balance of the recipient before. Okay, and I'm just sort of thinking pseudocode right now. And so now I want to show you how to take this idea and turn it into something more concrete. So let's think about transfer. So if I'm going to call transfer, I need to give it a recipient and an amount. Right? And in most programming languages, you'd say, oh, I have a variable here. I better say what that variable is. So I might be tempted to do something like, address recipient. And uint amount, right? Define these things. This is what I would do if I was writing a test case. I would define these things, I would call transfer, and then I would have some kind of assert message here, or assert statement that checks that the balance increases. And that's what our rule in CVL is going to look like mostly. This is sort of, I think the thing I'm going to show you now is, in some sense, the magic power of the Sartora prover. And that's that I don't have to actually write down what the recipient is. And I don't have to write down what the amount is. When I run the prover on a rule, if I have undefined variables, like I have here, recipient and amount, instead of giving undefined behavior, the Sartori prover is going to try every possible combination, every possible recipient address, every possible integer amount. And you might say, well, that's very close to an infinite number of things. And in some cases, it is an infinite number of things. So the prover isn't actually going to generate every possible test case and test them. Instead, it's going to sort of generate a formula from the specification, from the code, and solve that formula to try and find counterexamples. But effectively, you can think of it as trying every possible value of the recipient and every possible value of the amount. Okay, so I've declared these variables here. I haven't defined them. Then I'm going to want to call transfer and pass it the recipient variable and the amount, and the prover will call transfer in every way it possibly can. And then let's think about the assertion at the end. So I'm not going to do actually the whole transfer just to start with. Let's just assert that the recipient's balance increases. Okay, by amount. Okay, so what I would like to say is something like the balance after the transfer is the balance before the transfer plus the amount. So the way I get balances from an ERC20 contract is I call balance of. And balance of here should be the balance after the transfer. In order to compare it to the old balance, I need to record the old balance. So here I'm going to define a variable, balance before, and define that as the balance of the recipient. All right, then I'm going to call transfer. And then I'm going to assert that the balance of the recipient is equal to the balance before plus amount. Okay. And I like to always try and provide an assert message. So the idea here, we're checking that the balance of the recipient must increase by amount. And so I'll provide at the end of the assertion, I could put a semicolon here. If I put a comma, I can put a string that gives me the assertion message. Okay, and so I might say something like transfer recipient amount must increase recipient's balance by amount. And I'm now behind my Zoom window, so let me move that over. Okay, and so if we have a violation, the report will output this string. Okay, and then I can delete this comment because it says the same thing. I've written it in a couple places. This isn't even, I could put a comment up here. I'll just delete that because again, this assertion message sort of tells me everything I need to know. All right, we're not quite done here. So I'm kind of walking through the steps as I think about this. There's one or two more things we need to do for this rule before we're ready to run it. One thing I like to do, I like to have, with these kinds of rules where I'm checking a single method specification, I kind of like to have a little symmetry where I check things before, do the operation, and then check things after. And so here, instead of calling balance of right in the assertion, I tend to prefer to just create a variable to store that. And then I can do balance after. Check that balance after is balance before plus amount. There's two other things I want to mention, and then we can run this and see what happens. So the first thing is one of the important, one source of bugs that often comes up, this came up more frequently before Solidity 8, but still a lot of contracts use unchecked code, is we might have to worry about overflow. And so the contract, when I call transfer, might have an overflow bug in it, and I would like to catch that overflow bug here. But if I just have a uint, then when I do this addition, I might have an overflow here as well, and I don't want to have that. I want to actually notice, I want to get a counterexample. I want this assertion to fail if there's an overflow. So CVL has a special type called mathInt. And unlike the uint type, which has a fixed size, you can only store numbers from 0 to the 256 or whatever. Mathint represents actually a mathematical integer. It can have any value from -infinity to infinity, not including -infinity or infinity, but any number you can write down, mathint can be. And so I'm going to use mathint to store my balance before and my balance after. That way, I know this addition is the addition that I actually intended. This is almost always what I want. I'm not going to use mathint for amount because I'm going to pass the amount into this solidity function, and transfer doesn't know how to handle, arbitrarily large integers. So the input to my function is going to be a uint, but the output I'm going to store as mathints, so that the math that I'm doing on the outputs is the math I expect. Okay, so that's one change I want to make. The other thing I have to do, we don't need it for this example, but in the next example we'll have to think about it, is the behavior of transfer depends on who the sender is, right? Because transfer transfers tokens from the sender to the recipient. And I haven't anywhere here written down who the sender is. CVL has a special type called env. It stands for environment. And it contains all of the normal Solidity global variables that you can use about the transaction. So the message sender, the block timestamp, those are the main ones that I usually use. But all of those extra properties are in a type called an environment. So I want to run this transfer in an arbitrary environment. So I'm going to declare a third variable here, e, which is an environment. And when I call a Solidity function from CVL, I have to pass in that environment so that it's clear what environment I'm calling the function from. And again, I don't have to actually say what the sender is, because just as with any other variable, the approver will try every possible environment. That includes every possible message sender. But it does need to be declared. And one more thing before we go and run this. The way we've written this, I've actually called a couple of other methods of my contract. I've called balance of here twice. And so I might have to pass in an environment there as well, and here. And in fact, I don't really want necessarily the same, I don't want the constraint that it's the same message sender and block timestamp when I call balance of here as it is here as it is here. And so if I wanted to be really careful, I might do something like have environment E1 that I'm calling balance of with. I might have an environment E2 that I'm calling transfer with. I might have an environment E3 that I'm calling balance of with after. Now that's a bit of a pain. I don't want to have to do that every time. And I shouldn't have to, because balance of doesn't depend on who calls it. It doesn't, or shouldn't, right? Shouldn't, if I call balance of Alice, it shouldn't matter that it's me calling or that it's, Bob calling balance of. And it also doesn't depend on the block timestamp, for example, or really any property of the environment. It should always give me the same answer if I give it the same address. And so we have, there's a way to write down that some functions don't require an environment. They don't look at the message sender or the block timestamp or any of that. And that goes in what's called a methods block. So the methods block lets you declare certain methods and give properties of them. And the first property I'm going to show you is env free. So there is a method in this contract called balance of. It takes an address. So I give the spec here, returns a uint 256. And I'm going to mark it as env free. And this means that balance of doesn't depend on message sender, block timestamp, etc. Okay. So with that change, I can just have the one environment. I'm going to leave this environment. Transfer does depend on the environment. And I'm going to want to be able to talk about the sender of the transfer message. And so I'm going to leave that environment there. But because I've declared balance of env free, I don't need to include these other environments. Okay. So this now is a rule. I kind of walked through it piece by piece, but let's go through it once to just see what it says, and then we'll run it and see what it does. So to run this rule, I'm going to choose an arbitrary recipient, choose an arbitrary amount. I'm going to record the balance before in this math integer, the balance, delete that, the balance of the recipient before. I'm going to call transfer in an arbitrary environment with that arbitrary recipient and arbitrary amount. And then I'm going to record the balance after I've called transfer of the recipient. And finally, I'm going to check that the balance after the after calling transfer is whatever the balance was before increased by the amount. And so the prover, when I run this, it will take the contract, it will put it, there's another arbitrary thing here, it will put it into an arbitrary state. So if the contract has any fields, the prover will just choose arbitrary values for those fields. So we'll check that no matter what state the contract is in, no matter what recipient, no matter what amount, this rule should hold. Okay. So let's actually, I'm going to go run this. Are there any questions before I go on and run this and see what it does? Okay. All right, so let's run it and see what it does. So let me save my spec. I'm going to switch back over to my terminal here. Once again, move my window. Okay. So I'm in the ERC20 directory. I've got my terminal here. And the way you invoke the prover is you type Certora run. You give it the contract or the contracts that you want to verify. So in this case, we want to verify our basic ERC. And then you use the verify option, -- verify. Within a Solidity file, you can have multiple contracts. You need to specify which contract you want to verify, in this case, ERC20 basic, and what spec you want to verify it against, ERC20.spec. So if I run this, I get some output. One of the things that I haven't checked, so I'm getting an error here. The first thing the Certora run does, tries to compile the contract. In this case, there's a, in the ERC20 basic, there's a Solidity version specified. My Sol-C is a different version. And so I'm going to run this again and give this Solidity version. Actually, I'm going to do this before just so it's a little easier. And I have a binary, I have Sol-C different versions installed. So here you could give the path to your whichever Sol-C you want to use. Okay, so now I can run this. If I did things well, then it'll go. So what happens here? The prover is software as a service, so it's running on the cloud. But it first does some basic syntax checking. It then uploads the contract and the spec to our cloud service. It gives you this status page. I'll just open that up so you can see it. This just has some information about the job, or you can just wait until it finishes. It'll give you the link. And the output URL here gives us the actual report. Looks like the cloud actually, oh yeah, this is spitting out the results. So once I finish running this, this will spit out a bunch of information, including a table of rules and what was violated and what was not violated. I don't usually look at this output. I usually go to the verification report, which is what you see here, same as what I opened here. And this gives me, for all of the different tests, or all of the different rules, it gives me a report for each rule. And it's red with a thumbs down if the rule failed. It's green with a thumbs up if the rule succeeded. Now, I only wrote one rule, which was this transfer increases recipient balance. And there are actually two other rules here. And often the prover will generate some additional checks on its own, depending on what rules you write. In this case, we declared some functions were env free. So the prover is going to check, are these functions actually env free? And so that's what these two checks are. But here's the rule we wrote and that we're interested in right now. It failed. It's red. It's got a thumbs down. So that means either there's a problem with our rule or there's a problem with the code. And so the next step, once you've run the tool, is to go look at the counterexample it gives you if the rule fails and try and understand what's going on. So let's go through this process. So I can click on the rule that failed, and I see the assertion message that I wrote down here explaining what went wrong. I can see here the variables that I defined, but actually I find it more useful, the most useful thing is to dig into this call trace section. So the call trace tells me everything that happened when the prover ran the rule on the particular counterexample. So there's some contract setup stuff that the prover adds that just always happens. Some additional assumptions that are made. Don't worry about those. They'll show up every time. But then we see that, actually, maybe I can I, well, yeah, let me, okay, so here's our rule, and it's not quite, okay. So here's our rule, and we called three contract functions. We called balance of, we called transfer, and then we called balance of. And here we see sort of the call trace of what happened when I made those calls. So we call balance of recipient, assign it to balance before, call transfer, and then call balance after. And if we unfold these, we can see the arguments and return types to these things. And if we unfold them even further, we can see, you know, the whole sort of call trace, even down to the loads and stores from storage. So you can drill down kind of as much as you need here to see exactly what's going on as you're kind of walking through the code and trying to understand what happened. But I usually like to not drill all the way down first, because again, I like to think about interfaces first. And so I'll just drill down a little bit and see what happened. In fact, I could just look at these variables, but let's look at the call trace. So what happens? So the first thing we do is we call the prover as its counterexample took 401 as its owner. That's the recipient variable. Sorry, that's the message sender variable. Actually, it is both. It happened to choose an example where the sender and the recipient were the same. Anyway, it calls balance of with the owner. It gets the result 15. Then it calls transfer. The number of tokens it wants to transfer is 2. And then that returns true, which for an ERC20, transfer returning true means the transfer should have succeeded. And then it checks the balance afterwards, and it gets a balance of 15. So this is a little weird, right? Because we started with 15 tokens. We transferred 2 more tokens to the recipient. And then we ended with the same number of tokens, 15. And so our assertion that the balance after actually increased by the amount, that's not true, because 15 plus 2 is not 15. Okay. So I wonder if anybody sees why this went wrong. Like, what's the problem here? Is this a buggy contract? This is my my former life as a teacher is kicking in here. I'm taking a question for the audience. So think about this for a second. Does anybody see why?
People are responding, Mike. People are responding on the text.
Oh, great. Can Narit or Yura, can you guys read off some of the questions as they come in?
Yes, yeah, yeah, we have the answers on the chat, and sender and receiver are the same. So
yeah, so if I send from 401, if I try and transfer from 401 to 401, then of course 401's balance is not going to increase, right? Can't transfer to myself and increase my own balance. That's not how it's supposed to work. So in this case, the bug is not a bug.
The answer is by bow tie heron.
Okay, thank you. And yeah, so in this case, this is not a bug in the code. This is exactly how the ERC20 should work. It's a bug in our specification. So if we go back and look at our specification, transfer isn't always supposed to increase the recipient's balance. It's only supposed to increase the recipient's balance if the sender is not the same as the recipient. So let's update our rule to add that requirement. So I'm going to add another variable here, address sender. Okay. And I want to require, I only want to see a counterexample if the sender is different from the recipient. And remember, the sender is one of the variables in this environment that we're passing to transfer. And so I want to require here that the message sender is not equal to the recipient. And actually, I didn't need to declare a sender here because the environment contains a sender. Sometimes I'll do it this way. Other times I'll do something like here up top, I might say require sender not equals recipient. And then here, require that the message sender is equal to the sender. It's a matter of style. You know, this is just like writing any program. There's lots of ways of writing the same thing. But we've now updated the rule. The require statement in CVL says, ignore any counterexamples that don't satisfy this property. All right, this test should only apply when the sender is not the recipient. So let's run this again. While this is running, it'll take not too long. These are, as a simple contract, it'll run pretty quickly. On more complicated contracts, sometimes running the verify will take a couple minutes. On very complicated contracts, sometimes it can take over an hour. Maybe we'll have time to actually go through some complicated examples and see how you would deal with those long runs. Or occasionally, right, the solver can time out. We are in principle checking an infinite number of things, and sometimes that takes forever. And we'll talk about how to sort of still make progress if that's the case. I'll also mention, so I've run this a second time, so I'm going to get a second report. All of the reports are listed if you go to prover.certora.com. I've already logged in, but the first time you log in, it'll ask you for your Certora key, and you can just put that in there. And this lists all of the jobs that you've run and sort of what their status is. So this is the first job that I ran for you guys that we just looked at. This is the job that I just ran. Actually looks like it finished. And one other thing I'll mention just while we're looking at this list. In practice, while you're working with the tool, you end up generating a lot of runs. So there's an argument for the Certora run command, which is -- message. And if you provide that, you can just provide any string you want here. And that will show up here on the portal, and that can help you sort of keep track of which run is which. But anyway, this run has succeeded. So we can go look at the report. And now we see that indeed, transfer increases recipient balance, passed. There's no report here, right? The report gets generated when the rule fails to give you, here's exactly the set of variables when the rule fails. In this case, the prover could not find any counterexample where the rule did fail. And so there's nothing to report. We get a green check mark that says, in all cases with all values of the variables, this rule now passed. Okay. Questions? Pause for questions here. Are there any questions on Discord or Zoom that we should address, or shall I move on?
There are high-level questions. I don't know if we're going to address. I think Ernesto asked about which part of the EVM is the hardest to model with the SMT? I think that's one high-level question. Nurit, are there more?
No, I think no.
Actually,
Yeah.
I will ask a question like related with this example of sender and recipient. In this case, for what I understood, this require of sender different than recipient. It just ignore the counter examples that don't fulfill this condition, right? But
Yep,
what if I want to create like being more specific on the how's it called, the properties, let's say, and apart from having the last assert, also saying, but when the sender and the recipient are the same, I also want to check that the balance is the same at that point.
Yeah, that's a great question. I'll get to that. I was planning to get to that in my next example. Okay. Quickly, but great question. Thank you for asking it. And let me just quickly answer the other question that came up, which is nonlinear math is difficult for the solver. Sometimes a lot of storage accesses are difficult for the solver. There are a few other things that are difficult and can lead to timeouts. We actually have a page in the documentation which talks about what kinds of timeouts sometimes come up and how to address them. And maybe we'll get more into that in the next few sessions. Okay, so let's continue on with the specification. I wonder if anyone is concerned about this specification. What does this spec say? It says that no matter what, if I call transfer, then the recipient's balance is going to increase by whatever amount I provide. Is this something that makes sense? Should this rule pass? Does that, or this is a very leading question. Does anybody think this rule maybe shouldn't pass and have a reason why? Can you think of a case where I call transfer with an amount and yet the recipient's balance doesn't go up? Besides, of course, the one we've already seen where the sender is the recipient. I'm putting you guys on the spot. There
you have an answer from both Heron, balance less than amount.
Yeah. So I would be surprised if I tried to transfer some funds to Nait and I didn't have enough funds if her balance went up. So why does this rule pass on our ERC20 contract? Is it a bug in the contract? Is it a bug in the spec? Is it something else? Well, the actual answer is there's this turns out to be a feature, and as you work with the spec language, you'll discover you actually want it to work this way. There is an implicit require here that the transaction actually succeeds. So if transfer reverts, it doesn't report a counterexample. And that's usually what you want, because if a transaction reverts, it doesn't change storage, right? And so it has no effect, and you don't usually care what happened in that reverting transaction. Okay. Occasionally you do, though, want to consider counterexamples. You might want to say, I actually want this example to revert in a certain case. And so a feature I'll show you is when you call a contract method in CVL, you can add this notation @with revert. And what that says is that tells the prover, even if this function call reverts, I still want you to consider the counterexample, and I still want you to check this assertion. Okay. And so if we run this one more time, and I'll provide the message added with revert. So now if I run this with, oh, I backed up too much. Let me re-add my Sol C here. So now if I run this verification one more time, it'll take a minute, but we'll see that it will fail. So this is queued. It might take a minute. The last one took a minute. And we'll see that it fails in exactly the case that, sorry, was it Botan suggested, which is if the balance is too low, then the transfer will revert, and then we'll get a counterexample because the recipient's balance will not increase on the reverting transfer. Okay, let's just, still taking a minute to queue. So any questions about that? All right. So I think, give me 1 second. So I think what I want to do is take a short break. We've been going for 45 minutes, 50 minutes almost. So let's take a short break. You guys can take a pause. And what I'd like you to think about during the break is this specification here. This is not a complete specification for how transfer should work. All it does is checks that the recipient's balance increases by the given amount, but we actually care about a lot of other things. So let's take a 5-minute break, and I'll leave you guys to play with this a little bit and maybe think about some other properties. And if you were to try and write a complete specification for transfer, what you might like to check. And then we'll come back in 5 minutes and we'll go through a more complete specification of transfer. I'll show you a few more features and we'll continue from there. Okay, so 5-minute break, and I'll see you shortly. Okay.
Mike, there is, I don't know if you answer a question about what about contracts that require other contracts that exist, and can we verify those, or do we need to add a setup function? Also, can we run the prover in a network forking mode? I don't understand
Yeah, so great question. And I've just during the break read through the questions on Zoom and collected some that haven't been answered. So let me start by going through those. And I was just reading through the Zoom one. So if there are some that showed up on Discord, maybe Nurit can ask me those as well. But let me go through some of the questions that came up. Let me share my screen again. Okay, so the first question that came up, or I'm not sure if it was first, but one of the questions that came up, some of you may have seen a different syntax here for these arbitrary parameters. So instead of putting these arbitrary variables in the body, another style that you can use is to declare them as parameters to the rule. So I can do something like this instead of that. So I can just make them look like method arguments instead of like variables. It works the same way either way. The prover will choose arbitrary values for the arguments to the rule. We'll also choose arbitrary values for undefined variables. And so it's just a matter of style. Lately, the style I've been using for myself is something like this. If I have a couple of parameters, just because it gives me a little more space, but it's just a question of style. Whatever. We haven't developed a style guide yet at Certora, but whatever style you prefer is fine. Another question that came up, more of a higher level question, is when I run the prover, what actually happens? Is this doing fuzzing? Is it doing symbolic execution? What's it doing? How is it solving this, and what guarantees do I get? And the answer is, what it's doing is it is taking the specification and the contract and turning them into a logical formula. And then it is solving that logical formula. It is asking, is this formula satisfiable? Are there any values of these variables that can cause this assertion to fail? And then we hand that off to third-party software called an SMT solver. And the guarantees we get from that is, if there is a counterexample, we will report a counterexample. Or in other words, if we say this rule is successfully verified, that means this rule holds. With whatever assumptions we've made, this assertion is guaranteed to hold. So that's why we call it the prover. It actually outputs, it doesn't output, but it constructs a proof that this rule is always true. This assertion is always true under the assumptions that we have. If it's successful, and if it's not successful, it will give us a counterexample. So this is more powerful than fuzzing. It's not searching for a counterexample using, that might give up without, and say things are fine. If you get a green check mark, you know that this property holds. Again, subject to whatever assumptions you've made and whatever setup you've done. If I made an assumption here that's not true, well, then the rule can still pass. And in fact, that was one of the other questions, was what happens if I do something here, like add another required statement that the sender is equal to the recipient, right? So in other words, what happens if I have multiple requirements that are impossible to satisfy together? So what happens in this case is there is no counterexample, right? It is impossible for this assertion to fail. Of course, it's impossible for a stupid reason, which is there are no examples at all that could either pass or fail, because they all either get ruled out by this first requirement or the second requirement. This is what we call a vacuous rule. It's an assertion that passes, but only because it doesn't say anything at all. And we actually have some tools for checking if rules are vacuous. I'm not planning to go into those today, but there's some information in the documentation, and we can send out a link to that. But the answer is, if I write the wrong requires, all I'm saying here is if you somehow find a counterexample where the sender is both equal to and not equal to the recipient, well, then anything you want to be true is true. Okay, another question that came up was, a quick question. Somebody asked, can I share the spec code? And during the break, I checked in the version that I have and pushed it. So if you pull, you'll get to see the demo as it was at the end of the before the break. Okay, other questions that came up. A couple of people asked about this environment here, this enve. So let me just explain that one more time. The environment here, or in general, an environment contains things like the message sender, the block timestamp, the transaction ID, the message value, all of the additional variables that you can look at in Solidity that aren't explicitly passed as arguments. Those are all wrapped up in the environment. And if a function depends on the environment, you have to explicitly pass that environment in. And that lets you do things like what we've done here on line 18, which is put constraints on the environment. I only want to consider examples where the message sender for this transaction was the sender. So hopefully that answers that question. Let's see. Let me just go through my list here. Rule parameters, environments, vacuous rules we talked about, spec code. Check that in. Two other questions that came up. Actually, I want to save those two questions because they get to exactly what I wanted to talk about next. Are there any other questions that came up on Discord that should be answered?
No, I think we maybe on the multi-contract.
Okay, yeah, we'll get to multi-contract.
Yeah,
If we have multiple contracts, we'll talk about, you have to do some extra setup, some extra linking. We'll talk about that either tomorrow or Friday. I'm not totally sure. But in particular, one of the questions that came up was, if I don't have the code for a certain contract, what do I do? And we have a couple of options for that. One is you can make summarization. So you can say, I'm just going to assume that whatever this, I don't have the code for this, this other contract that I want to use, but I'm just going to assume that when I call this method, it's increasing or something like that. And we also have the ability to link together multiple contracts. And a third option we have is to sort of provide a list of possible contracts, and the prover will consider every possible version. But we'll go more into that in a future session. Okay. Any other questions before we move on? Anyone want to jump in with anything? Okay.
There's a question also from Peter. Can we run the prover in a network forking mode? I guess he means, can the prover connect to the actual blockchain and query the live state?
Oh, good question. The answer to that is no, the prover doesn't connect to the actual blockchain and check the state because it checks every possible state. We are actually working on a new product that will work that way, where we will use the same rules, but instead of trying to prove something, which doesn't, sometimes we time out something, sometimes some things are too hard for the prover. So we're working on a monitoring service where you write the same kinds of rules, but instead of proving them, you can just monitor the state of the blockchain and be notified if they change. So, so that's that answers that question. Okay. So before the break, I left you guys with a question, which is how might we expand this specification for transfer to be a little more complete? And so I'm going to hopefully get a chance to think about it. I think instead of, just for the sake of time, instead of asking you guys to name some things, although a few people did have some suggestions on Discord that I definitely will get to, let me go through and just add a few of the things that I might add. So one thing that we care about, we don't just care that the balance of the recipient goes up. We also care that those tokens came from the sender. And so we might also want to check that the balance of the sender goes down by the corresponding amount. So I might add variables here like balance sender before balance of sender. And then I'll change this to balance maybe recip before. And then do the same thing here. Right. And then I can add a second assertion here, right? So this should be balance of the recipient. And then I want a second assertion here that the balance of the sender afterwards goes down. Balance of the sender minus amount. And then I can add a note here. Transfer reduces sender's balance by amount. And actually, I actually like to be a little bit clearer in my messages here. Using, I like to say what the assertion must do this, or the function must have this effect that I think makes it a little clearer going back and reading what does an assertion actually say. And actually, I'll add one more thing to my messages here because we talked about, actually want to remove this with revert. We're only talking about successful transfers here. So this is a very similar to the rule that we just went through. This rule says the balance goes up. This rule says that the balance of the sender goes down. So that's another rule we might want. The other two things I want to do, get to some of the, for this specification, get to some of the questions that came up. So the first thing we might do is, you may know that the ERC20 spec actually says that transfer should return a Boolean, and that Boolean should indicate whether the transfer was successful or not. And somebody asked about whether we can do sort of conditional assertions here. And so let me show you how to do that. So I'm going to save the result of this call to transfer so that we can branch on it. And I only actually want these things to hold if the transfer returns success. So I could say that in one of a couple of ways. And which one you choose is a little bit of a matter of style. So one thing I could do is I could say, I only care about the case where the transfer returns success. So I could just require success. Let me call this success instead of result. So I could just require success. And that would say, ignore any counterexamples where transfer returns false. But that might actually not be what I want to say, right? I may actually want to say something. This was a question that came up before the break. I may want to say something in the case where transfer returns false. I might want to say, well, if transfer returned false, then none of the balances should have changed. And so CVL, like other programming languages, has an if statement. And so I could do something like if success, and then in here, add these two assertions. And then I could have an else. And here I could assert balance recipient after is equal to the balance before. And then I might say something like unsuccessful transfer must not change the recipient's balance. Right, and similarly, I could do the same thing for sender. Right, so we support if-else blocks, and they work kind of how you would expect. You can, again, think of this as a program, and this assertion will apply if that success condition is true, and this assertion will apply if the success condition is false. One third way of saying the same thing, which I'll just mention because it's a nice syntax sometimes, is remove that just for now. A third syntax that you can use is this assertion here is any Boolean value. So you can use the normal and or operations, not, and so forth. CVL also has a couple of additional logical operations. One of them is implication. And so that's often useful if you want to assert that if something, then something else. So the way that looks is you can assert that success implies, and that's a equals, this should be read as implies, or if then. So this version would say, check that if success is true, then this expression is also true. And that's a nice little notation that I just wanted to show you. Yeah, okay. So let me actually, there was one more thing that somebody asked whether we could check, which I think was a great idea. Let me actually ask if people have, besides the recipient balance going up, the sender's balance going down, are there other things you might care about? Anyone want to suggest something? I'll just take the one I'm thinking of because somebody already suggested it. I should write down who. I think it was Bowtie Heron again. Anyway. Another thing we might want to check is not only does the sender's balance go up and the recipient's balance go down, but actually everybody else's balance should stay the same. And we can write that using the same kind of rule that we've done here. Now there's three addresses we're interested in. There's the sender, the recipient, and anybody else. So let's add another address here. Maybe I'll put this on another line now. And so I'll just call them anybody. And if I want to call them anybody else, I might want to add a requirement that they are different from the sender and different from the recipient. Anybody else is not the sender, and require anybody else is not the recipient. And then I can again store the balance of anybody else before. and do the same thing here. And then I could assert that that doesn't change. So assert balance other after equals balance other before. Okay. Transfer doesn't change anybody else's balance. Okay. So this is another powerful kind of rule. Again, because we have this sort of magic power of introducing a variable and the prover will check that it works no matter what value that variable takes, that lets us do these sort of universal rules that say, yeah, check everybody else's balance and make sure that it doesn't change. And that's an important kind of property to think about, is not only what does change and does it change correctly, but also making sure that things that aren't supposed to change don't change. Okay. So that's a couple of other ideas for transfer. I have a few other things that I might add to this. Actually, let me do some of those. We're running a little short on time, but that's okay. We can finish some things tomorrow. So another important kind of property, and we saw this a little bit with the with revert, is I may actually care under what conditions transfer reverts. And I'm going to create a separate rule here just to keep things separate. And I'm going to call it transfer revert conditions, because I'm not happy with an ERC20 token if I actually can't call transfer because it always reverts, right? So the previous rule would say, if I call it and it's successful, then it does the right thing. That's great. I can transfer my tokens, except there might be a denial of service or something that says, no, actually, no matter what you do, transfer reverts. And so we might want to be specific about the revert conditions. So we might want to call, if we want to check the revert conditions, now we need to call the with revert that I showed you earlier. Right, I might want to add with revert, and that's part of the reason I put this in a separate rule, is I really do want this to talk about the successful cases. So here I want to call transfer without revert. Here I want to call transfer with revert. And again, I would want to declare some of these variables. And then I might like to, so the feature that I want to show you is with revert. You might want to say something like, if the transaction reverts, then this, if it doesn't, then that, something like that. And CVL has a special variable called last reverted, which tells you whether the last method reverted or not. Let me get so in particular for transfer, I want to check that it does revert if the amount is too big, right? So here, maybe I'll use that implication notation. So I might want to say, if the amount is greater than from balance before, no, if the amount is greater than balance sender before, then it should be the case that last reverted, right? That the last transaction reverted. Right, there might be other cases where it reverts, so it should revert if there's overflow. So if the balance of the recipient before plus the amount is too big, what's too big? Well, greater than max in 256, which is another special notation in CVL. So this is an integer that represents the largest 2 to the 256. So if, let me again be careful. So transfer must revert if sender's balance is insufficient. And this would say transfer must revert if amount would cause overflow, something like that. Okay, so that's another case in which, so if the amount plus the balance before is too big, then it should be the case that the last transaction reverted. And there are, depending on the token you're verifying, there might be one other condition. There may be multiple other conditions. One of the reasons we don't have one ERC20 spec that we always use for verification is there's a million different flavors of ERC, and some of them are supposed to revert if you try and transfer to address 0, for example, and others are not supposed to revert. And so there's a lot of different flavors, which is why sometimes you need to write new specs. So let me add that last one though. If the recipient is 0, then it should be the case that we revert. Must revert if the recipient is 0, something like that. So this would be telling me that the transaction must revert in certain cases. We might also want to say that the transaction should only revert in certain cases. And if I wanted to do that, again, just as we did before, there's a couple of different ways I could write that. I could use an if-then statement. I could require these conditions and assert that last reverted is true. Let me just show you one more notation, which is, so let me write this. And that's a if and only if operation. So I could say that last reverted is true if and only if, which is less than equals greater than. So this should be read as if and only if. So if last reverted, then whatever's over here, and if whatever's over here, then last reverted. And the conditions for reverting are just what I wrote. I'll just move them around here. Either the amount is greater than the sender before, or there would be overflow, or the recipient is 0. And then I'm not going to recopy these comments, but this version here would say, if last reverted, then one of these three things is true, either this or this or this. And if one of these three things is true, then last reverted must also be true. And so this would replace all three of these assertions. And also would tell us that this is the only way that the transaction can revert. Okay, so that's another kind of condition that can be useful to check. This would prevent a contract that sort of does a denial of service by preventing you from withdrawing tokens or preventing you from transferring tokens or something like that. Okay. All right. So we have about 10 minutes left, a little less. So I want to leave you guys with a few things. We didn't get to everything I wanted to today, but I think that's fine. Feel free to, send me a message if you want me to go faster next time, and I may go faster anyway, or slower. Please just let me know. Give me feedback. That's helpful. Yeah, I think we have time. I want to do one more kind of rule because I think it's another powerful and useful feature that I want to show you, and that'll set us up well for tomorrow. So let's think just for a second. Let's say that I go to this this ERC20 interface, and I write complete specs, perfect, specs for all three of the mutation functions, right? Transfer always, decreases the recipient balance, or increases the recipient balance, decreases the sender, all, reverts in the right conditions. Same thing with transfer from and approve. Everything, all three of these functions work exactly the way they're supposed to. I write, very crisp specs. There may be other, that might not be enough to convince you that this is a good token, right? So just because these three functions work the way that they're supposed to, doesn't necessarily mean that the ERC20 token is actually going to be a good store of value, right? So there might be some other function, right? If I'm getting an arbitrary ERC and I want to check it, there might be some weird function that I could call, maybe that an admin could call, that's just going to change these balances around in some weird way. But it's not any of these three functions. These three functions all work exactly the way they should. So there's an additional kind of property that I want to say, which is something like only I can affect my balance. No matter what function you call, if the balance goes down, it's because I did it. And these kinds of rules are called parametric rules. And let me give you an example of how we might write that kind of rule. Let's write that down. So if the rule I want to check is only I can change my balance, or only owner can decrease balance. So if I were thinking just abstractly, how would I want to test this? Well, I might want to say, okay, I'm going to start off, I'm going to call some function, right? Just like I did with transfer, right? I'm going to, record some state. I'm going to call some function, and then I'm going to check that if the balance decreased, then the sender was the owner, right? Something like that. So CVL has a nice feature for writing exactly this kind of rule. So let me take some of the let me take some of my variables from before. So we're going to record the same kind of state. Let's have the recipient and the sender as before. Okay, and we'll save their balances. And actually, I only really care about the sender's balance. There's not really a recipient here. In fact, maybe I'll call them the owner. Okay, so I have some owner. I'm going to save their balance before. Okay, so I have an owner. They have some tokens. They have balance owner before. And then I want to call some function. And then I want to get their balance after. Right? And then I want to assert that if the balance before is bigger than the balance after, that it better be the case that the message sender, I need an environment to get the message sender, right? It better be the case that the message sender was in fact equal to the owner. And the message here is only the owner can decrease their own balance. Okay. So this is kind of what I'd like to say. And I could take this rule and just copy it for every method, although actually I don't know what every method is, so I can't really do that. So instead, I'm going to use a feature of CVL, which is I can declare a variable of a special type called method. And a method is something you can call, and the prover, just like with the owner, it's going to choose every possible owner. If I declare a method variable, it's going to choose every possible method that exists in the contract. And so we'll actually get a separate report. If we call this arbitrary method f, we'll get a separate report for every different method in the contract. And I need to also pass it an argument, and I want to pass it every possible argument. And the syntax for that is a special type called call data arg, and I'll call it args. And this type represents an arbitrary argument or set of arguments. This isn't just necessarily functions that take one argument, it's functions that take any number of arguments. So I'm going to pass in this args here. And so this rule, I won't take the time to run it because we're out of time. I'll show it to you next time, the results. But this rule will check every method give me a separate report for every method with every set of arguments, every environment, and it will do the same kind of check. It'll ensure that if the balance goes down, then the sender of the message for this arbitrary function was the owner. Astute observers will note that this isn't actually true of ERC20 contracts. It is possible to decrease somebody else's balance under certain conditions. I will leave that as an exercise. We'll go through the example more concretely, but think about that overnight. Let me, for the last minute, just switch back to my slides, and I'll put these slides up as well. I'll probably just check them into the repository. So today what we did is we went through a bunch of the statements that you can put in the prover. We talked about rules. We mostly focused on what I call unit test style rules, which are describing the method specifications. This is what a method should do. We talked very briefly about these high level rules. Only I can change my balance. That's a property of all the methods of the contract. Those are sometimes called parametric rules. We didn't get to invariance. I'll get to that tomorrow. What I'd like to encourage you to do between now and tomorrow's session, make sure you've installed the prover and are able to run it if you haven't done that already. I'll check in the demo again, so pull that and play around, add some properties. Think about how you would want to really correctly specify what this rule should say. Think about how you might specify the approve function and the transfer from function. And there's a bunch of tokens in the tokens directory of the ERC20. And so you can actually run your ERC20 spec against a bunch of those tokens and see, look at some of the counterexamples that come up and say, oh, wait, this token works a little differently. Is this counterexample actually something valid, or do I want to change my rules a little bit to handle how USDC handles blacklisting or whatever comes up? And if you want a challenge between now and tomorrow or after tomorrow, there are a couple of tokens in the bytecode directory. We haven't given you the source code. We've just given you the bytecode. And I'll promise you that there are bugs in both of them. And it might be a fun exercise to go and see if you can find the bugs by writing a good ERC20 spec and checking it. And I'll go through, I'll show you those tomorrow as well. Also between now and then, we'll keep an eye on Discord. There's office hours starting shortly. I'm going to take a short break, maybe 10 minutes, but I think others will be there to start answering questions. We have a forum if you want to ask questions offline or after the workshop. And the documentation is in progress, but there's a lot of good information in there. So I'll refer you to that as well. So thank you all. I guess we're at time, so I'm gonna stop here. I'll be back for office hours in 10 minutes. I can't remember if it's the same Zoom room or a different
same
one.
link, yes.
All right, same link. So stick around and ask questions. I'll be back in a little bit. And thank you all for coming. So I will see you in a little bit for office hours or tomorrow if you're coming then. All right.
Thank you, Mike. Thank you, Mike. There are still questions. If people, I don't know if people are left, but there are still questions on the right.
Yeah, maybe I should go through the questions that are in the Zoom and on Discord just for the recording before I step out for a break. So let me just scroll through those and answer them now.
So are you pushing your spec again, Mike?
Yeah, I'll push it after we do questions. Let's see where and actually I don't know, Nurit, Yoav, if you guys have been, or sorry, Yura, if you guys have been keeping an eye on questions and have any that you think should be answered, feel free to jump in.
I see one important question about interacting with, let's say, an underlying pre-existing token. We will see tomorrow such examples. This is, of course, a very common case. So yes, we can handle that.
Okay. Let's see. What else? Looks like that's most of the questions. Oh, it looks like a question that came up is integration with other programming languages. It sounds like the questioner was asking about Python or Java, which makes me think that they're asking about sort of other testing frameworks, or maybe things beyond smart contracts. Right now, we're focused on smart contracts, so Python and Java, not so much. The tool works with EVM bytecode, so we have good Solidity support. We're working on Viper support. The only reason that we don't magically get Viper support from the bytecode checking is that we also do a lot of static analysis of the Solidity code to make sure that, to help the prover avoid timeouts. And so there's some heuristics that work for Solidity, don't work yet well for Viper that we have, but we're working on that. We have longer term plans to try and apply our technology to blockchains that don't use EVM bytecode, but that's going to be a little while for us. So that was a question. I'll push somebody asked about, can we get the rules I just wrote? I'll push them to the Aave branch. Okay. Oh, somebody's asking about the Discord channel. I'll make sure to mention that tomorrow. Posting at the Discord channel obviously won't help.
Yeah,
and also we sent out.
Yeah.
Okay. Oh, great. Okay. Perfect. All right. So I'm gonna take a short break. I will push the demo, and I'll be back for office hours in a bit.